My name is Lena Max, and I have together with my colleagues Andreas Petersson and Per Hjalmarsson performed the study subsynchronous oscillations between full power converter wind farms, voltage source converters, HVDC links, and nuclear power plants. So starting with the presentation, I want to define what is a subsynchronous oscillation. And it is an electromechanical interaction, typically between the shaft of a large synchronous generator and between an electrical system that could either be a passive elements such as series compensated lines, or an active component such as a voltage source converter or something similar. And these oscillations are at frequencies below the nominal frequency of the system. This was first experienced in 1970 in the Mojave project when there was a subsynchronous oscillation including a plant and a series compensated lines. And later on also another incident has been experienced in 2009, then including a wind farm with a doubly fed induction generators and also in this case a series compensated line. And as Monica mentioned here in the introduction, we see a larger content of large grid-connected voltage source converters, and thereby there's also an increased risk of experiencing subsynchronous oscillations, including these converters. And there are different types of subsynchronous oscillations, then depending on which components that are included. We have the subsynchronous resonance, which is the oscillations between the mechanical system in the generator and a series compensated line. Then we also have this subsynchronous torsional interaction, which is the oscillations between the mechanical system in the generator and some kind of power electronic device. And it could either be, for example, an HVDC link, as in this example, or it could be a large wind farm or any other device. And then we also have this subsynchronous control instability, which is oscillations between a power electronic device and another object, for example, another converter or a series compensated line or any passive object. And the aim of the project is to gain a good understanding on how these voltage source converters, for example, HVDC links and full power converter wind farms, can affect the existence of problematic subsynchronous oscillations. And to do this, we first have a look on which different methods that can be used to evaluate the risk of these kind of oscillations. For these methods, the suitability will be evaluated for investigating subsynchronous oscillations between large synchronous generators and voltage source converters, which is the focus of this project. And there will also be a more detailed description about these grid-connected voltage source converters to better understand the function of these converters and then the possible interaction. And in the end, this method will be implemented on a generic test system, then focusing on the oscillations between large synchronous generators and voltage source converter. So looking at the different study methods, there's been quite a few different methods used, and it's a lot of research ongoing on using different methods. And we can be divided into analytical calculations, frequency scanning methods, and time domain simulations. And start looking at the analytical calculations. When performing these kind of studies, we need the equations for systems, and these are quite exact methods. The drawback is that we need the equations, and if the system grows a bit larger, the equations will be quite complex quite quickly. And also a possible drawback that often models of, for example, converters are given by the manufacturer as a black box model, and then the controls are not known, and analytical calculations can't be performed since we don't have the equations for it. So another way is to perform a frequency scanning, and that is basically to see the performance of the system at the different subsynchronous frequencies. And it can either be done to obtain the electrical damping, which is done in the complex torque method. And then we see from a large synchronous generator, the electrical damping of the system can be evaluated. And we can also have a look at the impedance at different frequencies. And this can be seen for different parts of the systems. And that can be done in two different ways, basically. And it could be either very simple impedance frequency scan that just includes circuit parameters, or it can be done by dynamic simulations, which includes controls and black box models. And this method has the advantage that it can handle larger systems, since it's based on simulation models, and you basically let the simulation program do the work. But if we have a system that have black box model or controls, it requires that you do one time domain simulation at each subsynchronous frequency. So it can be quite time consuming. And this, both analytical calculations and frequency scanning gives a risk of subsynchronous oscillation, or can indicate if there is likely to occur. But then also time domain simulations should be used to verify the results of the other study methods. And these time domain simulations also include non-linearities of the model, which the other methods don't do. So all these different methods have their advantages and disadvantages. For example, some can handle non-linear model, black box models. They can include controls and so on. And in this project, we are to focus on oscillations between a synchronous generator and voltage-source converters. And then we know that we're quite likely to get a black box model from any manufacturer. So the methods that we are looking at need to be able to handle the black box models. It also has to be able to include controls. So the methods of interest are the complex torque method, the impedance scanning by dynamic simulations, and the time domain simulations. And these are also the methods that will be evaluated with the generic test system and shown in more detail then. And when evaluating the risk of oscillations, including converters, we should have a closer look at the converters on the design and the control of the converters. And for a voltage source converter, a quite similar implementation is what is seen in the figure. We have two voltage source converters. We have a DC link in between, and they're connected to one AC system in each end. And this could typically be an HVDC transmission. We have two HVDC converters, and we have the DC link that could be the cable or the overhead line. And it could also be the converter inside a full power converter wind turbine, where one converter is connected to the generator and the other one to the grid. And common for voltage source converters is that they consist of force commutated valves that can operate independently of the AC grid. Looking into these voltage source converter boxes, there are many possible topologies to implement this. A simple one to start with is the two-level converter. It has 6 transistors here that will form 3 phase voltages. And And the aim of the converter is to form these AC voltages as given in the reference from the converter controller. And this two-level converter is a quite simple topology. It's very common for smaller converters, and it can be used for smaller wind turbine converters. For the larger wind turbines, there can be also other topologies of interest. One more possible topology is the modular multi-level converter. It's a bit more complex structure, and it's commonly used for higher power levels, higher voltage levels, and it's used in many of the new HVDC systems. And here the phase voltages are formed by connecting a suitable number of submodules to form the desired AC voltage. And the topologies, they look quite different, but the aim of the topologies, both converters are the same, and it is to form the three phase voltages to follow the reference that is given from the converter controller. And looking at the typical topology or the typical voltage source converter system that we saw previously, it looked very much like an HVDC transmission. But if we look into the wind park, it is a bit more complex system because the new large grid-connected wind farms consist of a large number of turbines. In each turbine, there is this voltage source converter, and it is also one transformer in each turbine, and it is connected to a collection grid, typically cable grid. That is then all these radials are collected in a collection point where we have one large transformer that is connected to the point of common coupling. And in the turbine, the control of the generator is made in each turbine. We have a generator side converter which will control the generator in the turbine to follow the active power reference that's given. And we have a grid side converter that is controlling the DC voltage on the DC link and also controls the reactive power towards the grid to a given set point. And then we also have the control of the park, which is made in the park controller. And the purpose of the park controller is to send suitable set points to each turbine and then make the whole wind farm act as a power park module, and then make sure that it follows the requirements in the grid code. So for the wind turbine, there are controls in two different places. It is both in the converter controller, in the turbine converter, and in the park controller. And when modeling this wind farm, it's not suitable to model maybe 50 turbines, but instead an aggregated model, converter model, maybe one or a few converters can be used to make the studies. And looking at the dynamic operation of the converter, the aim of the converter is often to control the active and the reactive power. And this could either be just a set point given to the converter, or it can be a result from the for a voltage controller. For example, a AC voltage controller can give the reactive power, and a DC voltage controller can give the active power. And from these reactive and active power controllers, there is a reference current that's the input to the inner current control. And the inner current control gives the reference voltages for the phases. That is the input to the voltage source converter. And these voltage references is the reference value that the converter valves are supposed to follow. So we can see that the difference between the topologies is here in the converter modulation. So the control, the active power control, reactive power control, and the inner current control is independent of the converter topology. Looking at the bandwidths of the different controllers, we can see that the converter modulation, it's dependent on the switching frequency, and it is generally from 1 kilohertz and above, a bit depending on the converter size. And then the inner current controller needs to be maybe 10 times slower, and it's about below 1 kilohertz, but above the system frequency. And then we have the outer controllers, which can be the controller that determines how the converter operates against the grid. So it could be, if it's AC voltage control, it can be a DC voltage control, or it could be, for example, if the converter should operate as a synchronous generator, it's included in this controller. And looking at the range of subsynchronous oscillations, you can see that it is below 50 Hertz, and it will then be in the same range as these outer controllers. And it should also be noted that there is usually a phase lock loop in the converter control, which is also below 50 Hertz and then in the same range as the subsynchronous oscillations. So looking at this, it can be seen that what will affect the risk of subsynchronous oscillations for the converters is the slower part of the controller, the outer control loops and the phase lock loop. So looking at this, we are going to evaluate the risk of subsynchronous oscillations using this generic test system. And it's a quite simple system. We have a large generator connected to an equivalent grid, which is the black arrow here in the figure. And then we have a voltage source converter connected to the generator bus through an impedance. We have one transformer between the voltage source converter and the transmission system, which is the case for, if we have an HVDC converter. We have known torsional modes for the generator at 16 Hertz and 28 Hertz. And the purpose of this system is to evaluate the test methods and have an illustration of the possible results using the different methods. And if we start using the complex torque method, we will get an electric damping seen from the rotor of the synchronous generator. And it should be compared to the mechanical damping, and if it's negative, there is a risk of oscillations. And for the torsional modes, we know that the damping is very low and can be assumed to be 0. And since we look from the generator, we can't see the damping of the converter itself. But what we can do is to look at the electrical damping of the system with the converter connected and without the converter. So looking here at the results from this case, we see that we have the red curve here, which is the electrical damping without the converter. And the blue curve is the electrical damping with the converter. And here it can be seen that having the converter in the system will decrease the electrical damping, and it will increase the risk of oscillations at both the torsional modes 16 Hertz and 28 Hertz. And also looks at the impedance at different frequencies. And for impedance scanning, it can be chosen to be done anywhere in the system. And here we are choosing to do it from the generator bus towards the voltage source converter. And looking at the results, we see that we have a small positive resistance at the subsynchronous frequencies. But that results by this alone makes it hard to evaluate the risk of possible subsynchronous oscillations. But we saw from the electrical damping that there is a risk for subsynchronous oscillations. And to evaluate this or to verify this, we make a high impedance fault that's made to trigger these kinds of oscillations. So resulting from time domain simulations, we can see here that we have we make a fault, and then we have some quite slow oscillations. We see the rotational speed of the generator in the top plot here, and then we have the active power from the generator and the converter, and also the reactive power. So you can see that the large initial transients in active and reactive power, they are damped quite well. But then we have oscillations at about 28 Hertz that are amplified. And we can see that the rotational, it also includes the rotational speed here of the generator. And looking at the active and reactive power for the voltage source converter, you can see that there are oscillations in the reactive power, but not in the active power. So thereby it's assumed that it's the reactive power controller, in this case an AC voltage controller, that is the reason for these oscillations. Since we suspect that it's the AC voltage controller that it is the reason for the oscillations, we do two different variations of the control parameters. The first one is to decrease the gain of the controller, and the second one is to change to reactive power controller. And looking at the results here, we will, from the original blue curve, we will get the green curve with a decreased AC voltage gain, and the black curve by changing to reactive power controller. And we can see that the control parameters has a large impact on the electrical damping, and also that the damping will increase by these modifications. And it can also be seen if we look on the electrical, the impedance, the impedance of the voltage source converter. You can see in the left plot, the red curve, that by decreasing the gain of the AC controller, the resistance increases, which means that we have a higher damping. And also by changing to a reactive power controller with a constant reactive set point, which is the green curve, we get an even higher electrical damping and a reduced risk for oscillations.
Lena, it's about time to wrap up to make room for some questions.
Okay, that's good. So we can see that by changing control parameters, we can decrease the risk of oscillations. We can also see here that the impact of grid strength is quite high. Having a strong grid will decrease the risk of oscillations, or will decrease the impact of the voltage source converter. And also, if we have an additional transformer, which is the case if we have a voltage source, if we have a wind farm instead, it will be larger impedance between the generator and the voltage source converter, and then the risk of subsynchronous oscillations will be decreased. But in this case, we have a AC voltage controller that has a bad stability, but no subsynchronous amplified oscillations. So to wrap it up here, the risk for subsynchronous oscillations is that if we have a strong grid, we'll reduce the risk. A larger impedance between the generator and the converter will also reduce the risk. And the controller has a very large impact on the risk of oscillations. And the control methods. The complex torque method is very good if we have a large synchronous generator. Then we can see the damping from the generator, and we can show the impact that the converter will give on the damping. The impedance scanning is good if we don't have a synchronous generator, and it can show the if you make a change in one object, you can show the impact of that by looking at the impedance. And time domain simulation should be used to verify the results. So, thank you.
Thank you very much, Lena, and a very good summary there in the last slides. We have one question Zhongfei Wang. Please ask your question.
Okay. Hello, can you hear me?
Yes.
Yes, we can hear you.
Yeah, I thought I just type in my questions through the chat window.
Yes.
I'm wondering, in this study, you mentioned you used the black box model, but you also mentioned you changed the controller parameters.
Yeah.
So which control parameter can you change with this black box model?
In the test system, we have our own model.
Oh, okay. Your own model. Okay,
so it's just a model that we can do whatever.
Okay. Then what is the bandwidth of your PLL, this your own model?
I don't remember, but we tested a few different models, a few different bandwidths, but it didn't cause any oscillations just to change that one. So I can have a look at it, but I don't remember exactly the bandwidth.
Okay. Yeah, once I had a talk with the wind turbine manufacturers, they told me the AC voltage control can also induce some instabilities. Have you seen something like that? Okay.
The AC voltage controller, yeah, in the test system we had, it was actually the AC voltage controller that caused the instability.
Which at the turbine level or at plant level?
Now we just had one converter, and I think the AC voltage controller in the wind farm is usually at the plant level.
Yes, that one is usually very slow.
Yeah.
So I guess that one can be different from the single converter case.
Yeah.
Okay. Yeah. Okay. Thank you.
Thank you.
Thank you. And then Reza.
Thank you, Lena, for a nice presentation. So my question is, because the title, or maybe terminology, or I don't know what to call it, because what you said is like I forgot the title of your presentation, but it was something about subsynchronous resonance.
Subsynchronous oscillations.
Sorry, oscillations, yeah.
Yeah.
But is it because it seems that control, or control mode are exciting, or is it like better to call it control mode instability, or a still subsynchronous instability? Because I know that this comes from the generators and so on, but still it seems it's because of like improper control tuning.
Yes, but they have the different definitions here. You see the page. So subsynchronous control instability is when you don't have a generator included. In this case, because you can have oscillations between, for example, HVDC and the wind farm. If they try to, for example, control the AC voltage at the same bus, it can be issues. But in the test system that we used, and what we're looking at is the red version here, which is the oscillations between the mechanical system in the generator and the HVDC link. And then if it's usually the control that in the HVDC link or the wind farm that will give these oscillations.
Yeah. Okay. Thank you.